Okay, in this video I'd like to provide a little bit of an update for the types of questions that you see towards the end of our Test 2 review document. We're again focusing on functions and their behavior, and this time we're looking at linear functions. And I had a few questions about how to approach a problem like this. But before we get into that, I do want to point out too that I've started to redevelop my test number 2 that we're going to be taking on Thursday of next week. And here's an outline of the types of questions that I'm fairly certain will show up on the test. So of course we'll have to evaluate functions based on function notation and graph. So you have to understand how to evaluate functions and interpret them from the graph. So we saw those on day 19. I have questions on determining whether functions are even or odd. We practiced that on day 20. And then questions on increasing versus decreasing. That was day 21. And this was all last week. Then at the start of this week, we started talking about the difference quotient. We spent a day on that on Monday. We also revisited maximum and minimums, or maxima and minima, known as extreme values. We saw that last week, but also revisited it a little bit this week. And then for the last few days, we've been focusing on applications of functions or real-world scenarios. And so that was from Monday and then again on Wednesday and Thursday. I think, or maybe I'm getting my days mixed up, but day 22 and 24 through 25, that's when we spoke about them. Today we're going to focus a little bit more on linear equations, and you will see questions similar to those on the test next Thursday as well. So make a note of it that this is what's going to show up on the test as of right now, and pay close attention to each day. You can refer back to your notes and decide if you need to spend more time practicing those or not. The numbers down here, if you saw that, I'm also putting together a practice test or a review packet, if you will. And based on the current configurations, the numbers in the packet that are listed here would be no calc questions, and the numbers that are listed here are going to be calc permitted. My plan is to be back in the classroom tomorrow, Friday, and during our shortened day, I'll hopefully provide some more clarification there. So anyway, back to this question at hand. This corresponds to Chapter 4, Section 1, number 31, and it does show up in our assignment for this week. We have to answer all 6 of these parts based on the given function. Now, we don't know the equation of the function. We don't know the equation that generated this shape, but based on this picture and the data points that are given, I think we can answer these problems no real difficulty here. So in part A, B, and C, solve f of x equals 40. Well, remember f of x is the result of the function, or in other words, the y coordinate. So when the instructions simply say to solve the function equals 40, or solve for x essentially, when does f of x equal 40? Well, we can look at our graph here and notice that the y value is equal to 40 when x is equal to 24. And that's what we're looking for. To solve this equation, we're finding the x value that makes our y value, or our function result, 40. Now, if this was a nonlinear equation, we might have a curve to it like this, and there might be more than one spot where the function is equal to 40. But since this is linear, maybe not all of the time, but most of the time, there will be just one solution. It's possible that there are no solutions and an infinite number of solutions, but not if there is some slope to this linear equation. So when does f of x equal 80? Well, we can simply say that x is equal to 72 for that one. And then finally, when does f of x equal 0? Again, when does the function equal 0? Well, that occurs when x is equal to negative 24. So there we go. Those first 3, I think, are pretty straightforward. Then the question becomes, when is the function greater than 40? Well, we know that the function equaled 40 when x was equal to 24. So now we need to shift our perspective a little bit. When will the function values be greater than 40? Well, the function values again exist on our y-axis, And if I'm looking at this portion of the graph, this is the section of the graph where our function values are going to be greater than 40. And now we have to pay close attention to our inequality symbol here. We don't want to know what x values make the equation equal to 40 and greater, but just strictly greater. So I would report, since this problem was written with an inequality, I would say that any x value greater than 24, so any x value to the right of 24 on our x-axis, anything over here, will generate a y value that is also greater than 40. So I would only answer this question with an inequality since the original problem was written in inequality, as an inequality. However, we should view the instructions in Math Excel. They may want this answer in interval notation since we've been using it almost exclusively in this class. So we'll remind ourselves that in interval notation we would say that x must exist for all within the group of numbers greater than 24 as we approach infinity. So I personally prefer this answer better because we use interval notation more frequently. However, I think Math Excel in this case does ask for our results in inequality notation. For part E, when is the function less than or equal to 80? Well, I would say something like this. I think that the x values that are less than or equal to 72, I'll switch to a different color here, right? When x is equal to 72, we produced a y value that was equal to 80, and that's good. And then any x value that's less than that will produce a result that is less than or equal to 80. So make sure that we include the x value of 72 this time. And with our interval notation, we would say that x must exist between negative infinity and 72, where the 72 is included. So those two answers mean the same thing. They're just written in slightly different form. And then lastly, and I'll clear this out just to make it a little bit more clear, when will the function be between 0 and 80? When is the function greater than 0 but also less than 80? Well, again, we're talking about function values, so y values that are greater than 0 are to the right of 24, and y values that are less than 80 exist to the left of the x value of 72. So in between here, or on our x-axis, in between negative 24 and positive 72, this is the domain for which the function results will be between 0 and 80. So in inequality notation, I might say something like this. 0 is less than, I'm sorry, not 0, but negative 24 is less than x, which must be less than 72. That's a good result in interval notation, I'm sorry, in inequality notation, but in interval notation, we would say something like this, that x must exist between negative 24 and 72. And we're not including the endpoints here because of the strict inequality that was provided to us here. There was no equal sign with those inequalities, so the ends or endpoints of our boundary should not be included either. So hopefully that helps clarify this style of question. This one shouldn't be too challenging for you, especially once you understand the notation and the implication of each problem. Now in this example, we again have two linear functions. One of them is called f of x and one of them is called g of x. I don't recall if they're color-coded on your screen on Math Excel, but I'm going to say that f of x is our blue function that I'm trying to highlight here, and then we'll say that g of x is this green function here. Again, I'm sorry, the red function. We will again assume that these are linear equations that we don't know the functions to, but the graph should supply enough information to us. So for part A, again, we're being asked to solve the equation f of x equals g of x. Well, once again, when we solve the equation, we're trying to find the x values that make the y value claim, if you will, true. So when does the y value of f of x match the y value of g of x? That's fairly obvious right here. The only time that the y-coordinate and the y-coordinate of the g function and the y-coordinate of the f function are the same for the given x value occurs right at this position. So there are several times where the y-coordinates are the same for each function. Like in this case, the y-coordinate might be 3 here, and the y-coordinate might be 3 here, but it takes different x values to make that true. So this question is really asking us what x value can be used in the same, or in both equations to produce the same y result. And that happens to be, in this case, at -6. I hope that my description isn't making this more complicated than it needs to be, but bottom line is this: the two functions are equal to each other when they intersect. Now for part B, the question becomes, when is the function f of x greater than the function g of x? Or for what x values is the function f going to be greater than the function g? Well, to say that the function f is greater than the function g means that its y values have to be larger, or the y values have to be higher up on the y-axis. And that occurs right here. At this position, the f of x has to be larger. So in this section here, the f values are larger than the g values. So f was along this blue line, and g is now along this yellow line. But in each of these cases, the function f of x is greater than the function g of x. In all of these positions, the y value for f of x is greater than the g of x. As soon as we switch over past this data point, then the f of x function is actually less than the g of x function. It's below the g of x function. So to answer this question, we want to find all x values that satisfy this. And I would say that any x value that is less than -6 would satisfy this expression, because again, we're talking about this particular domain from here leftward. All of those x values produce y values in the f of x function that are greater. So this is an okay answer in inequality notation. I prefer my answers in interval notation. So as an interval, we would say all x values that exist between -infinity and -6. And we're not including -6 here. Had the instructions been written with a equal sign underneath the greater than symbol, then we would have made the switch to include the number 6, and we would have also included it here. And now for the last example that I wanted to cover in today's video is not meant to include this graph down below. That was actually a copy from the problem before, but we have this tax function that's a linear function. You'll notice that because there is no larger exponent on the x other than 1, and this function represents a person's tax bill, or how much taxes they owe based on their income. Now, if you were to take a financial algebra class, then you may learn this vocabulary a little bit more clearly, but essentially adjusted gross income is determined pretty early on when you start to calculate the amount of taxes that you owe at the end of each year, or when you file your taxes. So anyway, it's important to consider what domain would be appropriate for this particular function. Or in other words, what x values would be permitted for use with this function. And in the United States, we use a system called a progressive tax system, or progressive tax rate. And so folks that earn more money or have a larger gross income, they pay a larger percentage in taxes. And those that earn less money, that have a smaller income, they pay a lower percentage in taxes. So it's not that they pay less because they make less, but they also pay less because the percentage is lower as well. And so we use different formulas for each income bracket, if you will. And in this particular income bracket, the function that's being used, or the function that's being identified here, is only good for those that earn between $8,300 and $60,000 per year. So if we were to identify the domain of this function, we would say x, which represents our income, must exist between $8,350 and $60,200 inclusive. So that means we do have to include these endpoints. So only if your gross income is between these two numbers, or at precisely these two numbers, would you end up using this particular tax function. So I don't think I need to work through Part B, but we'll just talk about it quickly here. What is the single filer's tax bill if the adjusted income, gross income, is $21,000? Well, $21,000 does fall within this domain, so we do need to evaluate this tax function at the number $21,000. And you should recognize that to evaluate the tax bill at $21,000 simply means to replace any instance of X with $21,000 and determine the result. I'll leave that up to you. Question C, asking about the variables that are independent versus dependent. Well, we generally treat our X values as the independent variable, and so this question is asking, what do these X values represent? And therefore, our dependent variable would be the Y result, or in this case, the T variable. So I'll let you think about that and provide that answer as necessary. Now in Part D, I'm going to use the TI Inspired to show this because I think it would be worth your while to practice with it too. Graph the linear function over the domain specified. So I'm just going to graph this function as it's written in my Inspire, and I'm going to set the horizontal window between these two data points, and then I'll use the graph to fit as well. So let me set up the calculator now. Okay, so I have the function in here now, 0.15 times x minus 8350 plus 835. I think that looks about right. So I'll press enter. I don't see the graph, but if I jump into menu and adjust the window to the window setting, sorry, that's off the screen just a little bit. Let's see if I can fix that. The domain that we're worried about is between 8350 and 60,200. So if I change this to 8350 and 60,200, again, I can't see anything in the graph, but finally I'll go to the menu window and ask the calculator to fit the graph to that data. Now we can see that linear function. And to answer question, I believe it's E or D at this point, we can use the graph trace option. We would like to know what's the adjusted gross income if the tax bill is equal to 3708. Sorry, I misread that the first time. We can't use the trace function here. So we need to know the income if the bill or if the taxes come out to be 3708.55. So we can graph a second function here. 3708.55. So 3708.55. If we graph this second function, we can now find the point of intersection. We could also subtract 3708.55 from this expression and find the zero, but in order to remain in the window, I think this is a good option here. So we'll analyze the graph and find the intersection of these two, provide a lower boundary and an upper boundary. And evidently, when x is equal to 27,507, then the y value is equal to 3708.55. So when our income is $27,507, so when x is equal to $27,505, then our tax bill ends up being 3708.55. Sorry, 507. So I hope that that discussion helps you understand A through E. And finally, I'll let you think about the slope for just a moment. If we were to clean up this equation up here and distribute as necessary, the slope ends up being 0.15. And with our y-axis being taxed or taxable, let me say it differently, not taxable, but tax dollars, how much money we spend in taxes, and the x-axis ends up being income dollars, then our slope is essentially this tax dollar over income. What's that mean in terms of slope? 0.15 tax dollars per income dollar. I want you to sit and think about that and see if you can choose the result appropriately. And we'll talk about that tomorrow in class if there are further questions. Thanks again for watching, and I hope this helps, and my apologies for not being in class again today, but I do plan on being there tomorrow so that we can answer any of the questions that you have. Thanks again.